When we talk about confidence intervals of the mean, we're usually talking about an x-bar value derived from a sample, and we want to be able to say something about the mu associated with the population as a whole. So the x-bar plus or minus our z alpha over 2 times the standard error is a pretty common formula that we pick up and we memorize fairly quickly for calculating many of our confidence intervals based on the normal distribution. But it's also just as likely that the value we're dealing with isn't an x-bar from a sample of data, but it's more of a proportion. So a proportion, or an estimate of a p-hat, again, is a point estimate for the mean value of a proportion that is normally distributed. And the formula for that is just a little different because of the way we calculate the standard error on a proportion of p times q over n. Remember, q might be written as 1 minus p. You'll see it both ways. So the square root of pq over n is our standard error multiplied by the z for the alpha over 2, which is the same value we had in our x-bar calculation. So the way we calculate the proportions is a little bit different. The problem that arises here is that a proportion is not the same as a normal distribution. The normal distribution is what it is and it behaves the way it behaves because those two tails go off to infinity. To be normally distributed, you have to be able to take your tails off to infinity or the statistics don't work. In a proportion, the lowest your proportion can be is 0 and the highest it can be is 1. There are no tails. So when you're over there at the edge of the distribution, you run the risk of applying the thought process of an infinite tail to a distribution that doesn't actually have one. And you end up with an error when you're dealing with the statistical properties of proportions for confidence intervals. This graph is taken directly out of the DeVore text. This is copyright Cengage. I'm borrowing it for the purpose of this presentation. But if you take a look at this curve, what you see is the kind of error that occurs when you assign 95% probability curves to a proportion. So the line at the 95% across the top is our 95% probability. So we're trying to calculate a 95% confidence interval. That's what this graph shows. For other percentages, you'd have to draw the graph differently, obviously. But for a 95% confidence interval, you get an answer pretty close to what you expect if your p is in the mid-range. So a p of 0.5 plus or minus maybe 0.1 or 0.2, you're going to get the kind of result you would expect. But as this graph shows, as you move away from a p of 0.5, you get less and less accurate. So if your p is way down here at 0.1, okay, or 0.05, when you think you're calculating the 95% confidence interval using the standard formula, it turns out what you're actually calculating is about the 86% confidence interval. And that can make a big difference depending on the engineering problem that you're dealing with. You can think of this graph as a smooth curve starting down low on the left, coming up and peaking, and then dropping to the side. The reason it looks so jagged is because the curve is developed using a binomial distribution, which is a discrete distribution. So there's simply the blue lines connect the dots that derive from the discrete calculation of the binomial distribution. So you can think of it as a curve where the farther you get from 0.5, the larger your error as you go through. And that's, again, caused because when you're over here near 0 or up here near 1, you don't have that infinite tail going out the other side. So if you think of the confidence interval as plus and minus something, so if you're starting at a p of 0.05 and you're plus and minus 0.1, that implies your confidence interval spills into the negative territory, which it can't. And that's why at the edges, your 95% straight calculation of your confidence interval ends up introducing error into the formula because you're calculating a range of values that doesn't actually fit the description. So typically we have a way to adjust for that. We adjust that value using a more complicated formula. I know it looks like a mess, and it can take some time, but if you're careful in Excel, it's not hard to calculate. So it starts off with the basic term for the median value, so p hat plus or minus z squared over 2n, 1 plus z squared over n is the base value, and that becomes p, the median value. And that's plus or minus. That becomes a new point estimate, which by itself will already be different than p hat was. And then the interval itself, rather than just z times the standard error, gets a lot more complicated. It's z times the square root of standard error that includes z divided by 4n squared, and that's brought over the 1 plus z squared over n again. So the formula is more complicated. If we were statistics majors, we'd probably have to learn how to derive this formula and even prove that it's true. Fortunately, as engineers, we don't have to derive the formula, we just have to use it. But if you use this basic formula instead of the baseline formula you will taught, you can avoid the error associated with p's far from 0.5. If p is near 0.5 and you want to save some time, just go ahead and use the baseline formula. You'll get a reasonable answer. But when p is near 0 or near 1, make sure you're using the adjusted formula to make sure you come up with a confidence interval that's actually the level that you want. Because if you're reporting your interval as 95%, you don't want to have the data itself actually be only 86% or less, and have management move forward thinking they can have 95% confidence. We need that adjustment. So stay focused on this basic formula as you go through. When you're calculating proportion confidence intervals, make sure you're using the right set of formulas.